Okay, in this video I'm going to talk about the 9-point circle and the Euler line. So basically in the previous video I proved that the 9 points defining the 9-point circle lie on the same circle. So basically this were the midpoints of the sides of it. So we have an arbitrary triangle, then we take the midpoints of the sides, B, MA and MC, so the midpoints of the sides. Then we have the feet of the altitudes, so this point, this point, and this point. So these are 6 points, and now we take the midpoints of the segments connecting the vertices with the orthocenter. So the midpoint of this segment, the midpoint of this segment, and the midpoint of the segment. Yeah, and this so these eight points, so let me select them in blue. Yeah, so these 9 points that I selected in blue, these 9 points lie on the same circle. This I proved in the previous video, and this circle is called the 9-point circle. So in this video I'm going to show like how to find the, or not how to find, but like I will show what is the center of this circle, what is the radius of this circle, and some other properties. So, and it will be connected to the Euler line. So first we will use a well-known property of the orthocenter that that if we reflect the orthocenter symmetrically with respect to the sides, then it will be exactly on the circumcircle. So if you consider the circumcircle of the triangle, we have the orthocenter, right, the intersection point of the altitudes. Then if we reflect it with respect to the sides, then these points, the reflection points, would be exactly on the circumcircle. So this is kind of a well-known property, but like let's prove it. It's not difficult to prove. We just need to, well, I will prove for one of them, the other two would be similar. So we just need to calculate the angles. So this altitude, so we denote the angles of the triangle as alpha, beta, and gamma. So then this angle is equal to 90 degrees minus gamma, right, from this right triangle. Then we, so for now we forget that these are reflections, so we just extend the altitude until the intersection with the circumcircle, and we will prove that these two segments are equal to each other. So that's how we will establish that. And we consider now this. So now this angle is equal to this angle, because they're inscribed angles subtending the same arc, right? But this angle is equal to, from this right triangle, is equal to 90 degrees minus gamma, right? So therefore this angle is also 90 degrees minus gamma, and we have that these two angles are equal to each other. So because they are equal to each other, so I can remove this, not like we can show them on the picture that they are all three of them are equal to each other. So now we have these two triangles, right triangles with the same with the equal angles, so therefore they must be equal to each other. Or like we can also say that in this triangle, so in this triangle, the bisector is coinciding with the altitude, right? So like this is a bisector and also an altitude. So therefore it's an isosceles triangle, and this is also a median. So these segments are equal to each other, and so this exactly means that the symmetrical reflection of the orthocenter falls on the lies on the circumcircle. Okay, so now if we so I will remove now this. So we draw the circumcircle, and so we extend these altitudes and to the intersection with the circumcircle, and just as we established, so this segment is equal to this segment. So like there are no more I'm not sure how to denote this, because we already used a lot of notation for equal segments, but so let's color them in the same color. So this segment is equal to this segment. This segment is equal to this segment, and this segment is equal to this segment. Okay, so basically now we consider a homothety with the center in the orthocenter. So we consider, homothety with center, not a homothety, but the homothety, because it's the only homothety with this, with a given center and the given coefficient. So with the with center h, so the orthocenter, and the coefficient, the scaling coefficient, equal to 1/2, right? So we shrink, basically we shrink the plane with the center h, shrink everything with the center h. So then this point, so let's call it HB prime, right? So this would be HA prime, and this is H C prime. So under this homothety, so H A prime maps to H maps to H HB. So this is the point HB, the foot of the altitude. This is HA, and this is HC. Right, so HB prime maps to HB, and HC prime maps to HC. So this means that the whole triangle HA prime, HB prime, HC prime maps to HA, HB, HC, right? So, but this means that the circumcircle of this triangle, so the circumcircle of this triangle is this large circle omega, the same as the circumcircle of ABC. And so let's write this: the circumcircle of the triangle HA prime, HB prime, HC prime maps to the circumcircle of HA, HB, HC. So now the circumcircle of this triangle is just this large circle omega, the same as the circumcircle of ABC, and the circumcircle of HA, HB, and HC. So this is because these 3 points lie on the 9-point circle. We proved it in the last video. So the circumcircle of this triangle must coincide with the 9-point circle. So this is the omega 9. We will denote it. Omega 9 is the 9-point circle of the triangle ABC. So under this homothety, so in total under this homothety, the circumcircle of triangle ABC is mapped to the 9-point circle of this triangle ABC. So this means that in particular the center, so in particular the radius, so the radius so remember that the coefficient of the homothety is 2, so therefore the not 2, well, 1 over 2. So this means that the radius of the 9-point circle is exactly twice smaller than the radius of the circumcircle. So this means that the radius of the 9-point circle is equal to 1/2 of the radius of the circumcircle. So that's how we establish the radius, and now the center. So the center also, like under the homothety, if one circle is mapped to another circle, then the center of this circle must be mapped to the center of this circle. So this means that the center, so if we denote by O the circumcenter, and by O9 we denote the center, by O9 we denote the center of the circumcircle, of the 9-point circle. So this is O9. So then O9 must lie at the midpoint of the segment OH, right? Because with center H, so we consider the homothety with center H that shrinks the circle with center O to the 9-point circle with center O9, right? So therefore these two segments must be equal to each other. So O9, so the center of the 9-point circle O9, first it lies on the line OH, and then it is the midpoint. It is the midpoint. Yeah, so let's write this. O9 is equal to O9H. So it is the midpoint of the segment OH. So that is how we established where the center of the 9-point circle lies. And now we actually can consider another homothety, and this is kind of related to what I said at the end of the previous video. So because there is another homothety that maps the same two circles to each other. So if we consider now the midpoints of the triangle, right? So we know that this triangle, this internal triangle, is similar to the large triangle with the coefficient 1/2. So like it's twice smaller than the large triangle. But they're not only similar, but they're homothetic as well. So if we consider the centroid of the triangle, so we draw the medians and we consider their intersection point, which is centroid, like we denoted by G. So then the ratio of like in which centroid divides the medians, like it's well known that it's 2:1. So A MA, so A G over GMA is 2:1 ratio. And for the other medians as well. So so this means that if we consider a homothety, so if we consider the homothety with center G, centroid, and coefficient minus minus 1/2, right? So under this homothety, the triangle ABC would be mapped to the triangle MA, MB, MC, right? So like, yeah, so like the point A is mapped to the point MA, right? Because the ratio of these segments is 2:1, and so GMA is 1/2 of AG, but also like they lie on the different sides of G, so the coefficient is negative. So this is why we have the negative coefficient of the homothety. So basically, and from this it follows also that the circumcircle, so the circumcircle of this triangle is mapped to the circumcircle of this triangle. And the circumcircle of the triangle ABC, this is the same large circle omega. And the circumcircle of MA, MB, MC, this is again the 9-point circle, because we proved that all 9 points, so both the feet of the altitudes and the midpoints of all sides, they all lie on the same circle, on the 9-point circle. So this is again the 9-point circle omega 9. So omega is mapped to omega 9 again after this different homothety with negative coefficient. So this proves again, so again because the coefficient is -1/2, so we again established the radius. So the radius of the 9-point circle is twice smaller than the radius of the circumcircle of ABC. But this we already established previously. But now we also established where the center must lie. So from this homothety, again, so G, somewhere here we have the center O of the of the 9-point circle, of the circumcircle, and the center of the, well, it's kind of, there is not much place to display anything here on this picture. So somewhere here there should be this center O9, so such that O, G, and O9 lie on the same line, and G divides this segment with the ratio 2:1 because of this homothety. So under this homothety, also the center of the circumcircle O is mapped to the center of the 9-point circle O9. So therefore this center, so therefore O9 lies on the line OG, and the ratio, so OG over G O9 is 2:1. So now if we combine these two findings, what we established here and what we established here, where the center lies, so when we combine this together, we get that. So let's draw this separately. So now, like, I'm not even going to draw the triangle, so we have only the point. So we have the point, so initially we had the point H, the orthocenter, and the point O, so the circumcenter, and we established that O9 lies at the midpoint of this segment. So at the same line, OH and at the midpoint of this segment. So now we established that there is also a point there is also a point G, and it is located. So O9 also lies on the line OG. So there is a point G here. G, such that this to this is the ratio is 2 to 1. So so if we denote this by x, so G09, if we denote by x, then OG must be 2x, and this segment O9H must be 3x. So that's okay, so let's draw another picture, like larger. So basically what we have is that we have this line. So we have this line H O9 O, and we have here G. So the ratio is, so if this is x, then this is 2x, and this is 3x. So this is, so all these 4 points, they lie on the same line, and the segments that they divide are in these ratios. So, or G, O9, and H are collinear. Okay, but so now from this we actually as an unintentional corollary we proved that now if we forget about this point O9 and about the whole circle, the whole 9-point circle, so we get that O, G, and H are collinear in particular, right? So if all these 4 points lie on the same point, but in particular these 3 lie on the same point, on the same line as well, these 3 are collinear as well. Collinear. So again, we recall that O is the circumcenter of the triangle ABC, G is the centroid, the intersection point of the medians, and H is the orthocenter. So now we proved as an unintentional consequence that these 3 points are collinear, that the centroid, the circumcenter, and the orthocenter of any triangle are collinear. And this line on which all these these 3 points and also the 9-point center O9 lies, this line is called the Euler line. So this line, like this line is called the Euler line. Yeah, so yeah, and by the way, we not only proved that they're collinear, the 3 points, but we also proved the ratio. So the OG, so they're collinear, and OG, the ratio of OG to GH is equal to 2x to 4x. So this would be 1/2. So the centroid divides the segment of the segment connecting the circumcenter and the orthocenter in the ratio of 1 to 2. Yeah, so this is the Euler line, and the center of the 9-point circle also lies on this Euler line. Yeah, so that's it for this video.